This case, the side-side angle case, has its own subsection because we need to do a little bit more thinking here. I'm going to draw a generic triangle. Be careful not to make it look too much like a right triangle. I really have a hard time with that. And then I'm going to label the angles, alpha, beta, and gamma. And again, normally, or in the past, we've often called these A, B, and C. Now, when I have a triangle, when I'm drawing my own triangle, I usually draw a triangle that looks very much like this, even if the ratios are off, even if the angle sizes are weird, or this is going to be way out of scale. And the reason for that is that with this consistency, I have found that if I have A here and B here and C up here, I can always label my triangles given the angle sizes and the side lengths that I'm given in such a way that this particular case, the side-side angle case, is less problematic for me. And so what I'm given in a side-side angle case is either these two sides, and then so a side going around, another side going around, and then an angle, or this side here, and then another side, and then an angle. And the way I set these up whenever possible is to make it so that I'm given these two sides and this angle. And that just helps me with diagramming this problematic angle. We'll come to that in just a minute. So let's take a look at an example. We're going to be using the law of sines, and we're going to be solving the triangle. So I'm going to start by labeling my sides. I have a little a there, little b here, and a little c here. And now I need some measurements. And I'm hoping that I'm going to get angle A, side A, and then side B. So A, B, and angle A, side, side, angle. So what happens if we're given the following information? The angle we know, alpha, is 24 degrees. That's this angle right here, 24 degrees. The side opposite it is 3, and side B is 7. So I have a known angle size across from a known side length. That's my clue that I can use the law of sines. So I'll start by setting that ratio up. The sine of 24 degrees over 3 is equal to an equivalent relation. Now the only other one I have here is angle beta, or angle B, across from side with a side with the length 7. So I'm going to put 7 there. I'm going to have to use opposites, so I need the sine of angle beta here. Sine of beta. And then using algebra, I can rewrite this as 7 times the sine of 24 degrees all over 3 equals beta, equals the sine of beta, sorry, the sine of beta. Now, I want beta, so I'm going to basically take the inverse sine of both sides of this equation. And that gives me beta equals the sine inverse of whatever this works out to be. And this works out to be approximately 0.94905. Now, taking the sine inverse of that gives me 71.63200 degrees. So now I know how big beta is. For record keeping purposes, I'm just going to call that 71.6. And on the surface of it, it looks like we're done, at least finding this, this angle, right? We can now go in and find angle C and use the law of sines again to find side C. Unfortunately, there's a little bit of a problem here, and that is that this side is sufficiently short that there might actually be a second solution here. So I think what I'm going to do now is erase just this part because that information is all over here. And I'm going to redraw this triangle over in this space. Now I've drawn what I think is a reasonably good copy of this triangle over here. I've left a few of the labels off just because I want it to be kind of clear what I'm doing here. And I want to make the point that we've just arbitrarily put this side down over here. But in fact, it could be here. Then I'd still have, let's see, we called this, we said this was A equals 3. If this was our A instead, we would still have a side-side angle situation. And if I erase part of the sides here, I don't really want them anymore because I've already solved this triangle, or haven't finished solving it yet. I found this angle. From there, I can solve it using the law of sines. But I don't want to erase it completely because I want to use it as a reference. So I've made it dotted lines instead of solid lines. And so you can still see this, the triangle, the big outside triangle. That's the one we were working on over here. Now, like I said, we had arbitrarily assigned this to be our side A, but we could just have easily have made this our side A. And what happens if that's the case? Well, with our big outside triangle, we were able to find the measurement of this angle. That wasn't too hard. Turned out to be 71.6 thanks to some trigonometry, the law of sines. And so with that, we know something about this triangle. And that is that because if you're looking at this triangle, I wonder if I should highlight that. If you're looking at the highlighted triangle, then this side and this side have the same length. This is an isosceles triangle. And one of the things we know about isosceles triangles is that the angles across from the equal sides are also equal. So the angle across from this side of length 3 is 71.6, then the angle across from this side of length 3 is also going to be 71.6 degrees. And that doesn't at first appear to help us with this triangle, but in fact it does, because with this angle measure, this is a straight line here. I can find this angle measure. That's going to be 180 degrees minus 71.6 degrees. I'm going to use this much more accurate value here. So when I do this arithmetic, it may actually not be perfectly clear. It may not be absolutely accurate in appearance, but it will actually be more accurate than the arithmetic that I'm doing here. So bear with me. I'll put this into my calculator. And I get 108.36799978. So to round to 5 decimal places, I need to make that 99 at the end. I need to round both of those up, and I get 108.36800. So this angle right here is 108.4 degrees. Let's do that in green. 108.4. I'm going to hang on to this value, this more accurate value, in case I need it later. All right, now I have two angles and two sides. I have the angle across from here, the side across from this angle and the side across from this angle. So all I need now is this angle, this small angle in here, and the side across from that. I'm going to call this angle here, get the right color pen, we call this angle beta, we called it B. And then I'm going to call this one here beta prime, or B prime. And that's to distinguish it from the other B angle. This B here is not the same as this B here. B prime is a different angle. In this case, it happens to have the same measurement. But I'm looking at angle B prime, or beta prime, as a tool for finding this angle. And up here, I'm going to call this large angle, angle gamma, and this small angle, angle gamma prime. So that's C and C prime. So having solved this triangle, again, I haven't quite done that. I'm still missing these two pieces, but I can find them using the example I did on the previous, in the previous video. That's the big triangle. There's a second triangle here, and I have the side opposite the 24-degree angle. I have the side opposite an 108-degree angle, and I can use the same information, subtract these two angles from 180 to get this angle, and then find this third side, which would be little side C, whereas this whole C prime rather, whereas this whole thing was little side C. This little one here, this partial line segment is prime C prime, because it's across from angle gamma prime. So this was the tricky part about this situation. This was the SSA situation. The one that if you spelled it backwards in high school or junior high, you'd get in trouble, right? We're grown-ups here. We don't need to giggle about it. But it does help, for me anyway, it does help remind me that this is the situation where we might run into trouble. One thing you might always do is when you're trying to solve a triangle, draw your triangle, label your sides, figure out what your, sorry, that's the wrong, A equals here. I can't talk and write at the same time, apparently. Figure out which values you know, which ones you don't, which ones you need. And then always just check to see if there's a second triangle, right? Check to see if there's another place where that third side might go. And you can tell that that's a possibility because you've been given two sides and an angle, but not the angle included between those two sides. That's a side angle side situation. This is not a side angle side, it's a side angle, and those are different. Okay, so that's enough for this video. I know I didn't solve these triangles, but in this case, the point of the video was to point out that there are two potential answers here, and I've shown you how to find, or at least how to start finding the second answer. In our next video, we're going to talk about a new formula for the area of a triangle. I'll see you over there.